Hello students, good evening. Welcome to GATE Wallah. I am Venkat Rao, teaching theory of computation subject for GATE 2025. So we are continuing our lecture series. Today is our lecture number 12. So in the previous sessions we studied some of the concepts of theory of computation. We are in the topic of pushdown automata. Yesterday we started pushdown automata. Today's session is also continuation of the pushdown automata. Alright. So before going to start this, let me recap what we studied in the previous session about pushdown automata. So pushdown automata is one of the very important concept for GATE examination. We are getting so many questions in the GATE paper related to pushdown automata. Pushdown automata and context-free language. This topic is the second important topic for GATE examination point of view from the subject theory of computation. So in our yesterday session, I have given an introduction regarding pushdown automata. What is pushdown automata? What is its block diagram? What is its definition, formal definition, and how to design it? So all these things we studied. Let me recap this. Today we are going in depth on pushdown automata. Yesterday one is the introduction one. Today's session is about we are constructing the problems, some GATE level problems. Today's class. Right. So in yesterday's session, pushdown automata definition we studied, how pushdown automata is defined, acceptance mechanisms, what are the different acceptance methods present in pushdown automata, and configuration of the pushdown automata. So the basic block diagram of pushdown automata looks like this. We have an input tape. We have input tape here. And we have a stack. We have an input tape, we have a stack. What is the difference of pushdown automata compared to the finite automata? The difference majorly comes here is finite automata don't have a stack, pushdown automata having a stack. This is the major difference. That's why if you observe pushdown automata, finite automata having one stack. Finite automata having one stack. The total structure is called as pushdown automata. Due to this stack, what things we are going to handle? That is memory. Main limitation of finite automata is finite automata fails whenever memory is required. That too infinite memory. Finite automata can handle up to finite memory. Whenever the infinite memory is required, finite automata fails. That thing I discussed in yesterday's class through examples. So whenever comparison exists in the language, whenever there is a comparison in the language, at that time finite automata fails to accept languages, that to infinite comparison. So in order to handle infinite comparison, we are inserting a stack in the pushdown automata. Definitely the size of the stack here is infinite. Size of the stack here is infinite. So finite automata having one infinite stack. So the total structure is like this. Finite automata plus infinite stack together is called as pushdown automata. This is the structure of the pushdown automata. So finite automata having one stack. This total structure is called as pushdown automata. Right. So to construct this, to construct pushdown automata, we studied in last class formal definition. Formal definition is the actual and main important definition of pushdown automata. Whenever you want to construct any PDA, now onwards I will call this as a PDA. Whenever you want to construct any valid PDA, what are the things required? What things you need to include in that? What things we need to exclude from that? All this information is provided by this PDA formal definition. So the formal definition of PDA generally contains 7 things, 7 tuple. So here we have Q0 that is initial state. Q0 is the initial state here. So what are the 7 things? Q is set of states. Set of states. Sigma is input alphabet. Q0 is initial state. Delta is transition function. Q0 is the initial state. F is set of final states. And these 5 things, first 5 things are similar to the finite automata. Finite automata having 5 tuple. Here also we have 5 things plus additional 2 things. Those 2 things belongs to stack. So the last 2 things whatever is there, Z0 and tau, this belongs to the stack things. What is Z0 here? Initial stack element. Initially we have some element Z0 in the stack. So whenever PDA is doing pop operations, compared to the finite automata, we have a stack. So we do push pop operations with the stack. What PDA is doing? It is doing push pop operations with the stack. Whenever symbols are pushed into the stack, then sometimes symbols pop out from the stack. These push pop operations are the major additional operations which are there in the pushdown automata compared to the finite automata. Right. So Z0 is the initial stack symbol. Whenever we are doing pop operation, the moment Z0 encounters, we can conclude that all the things whatever we push, those are popped out. Next we have tau. Tau is called as stack alphabet. We are pushing some symbols into the stack, and we are going to pop some symbols from the stack. So this push pop operations together will lead some elements into the stack. The total number of symbols allowed into the stack is called as stack alphabet. So this total thing is called as tau. So this is the total structure of the PDA and its formal definition. This is what we studied completely in the previous session. Then acceptance methods. PDA mainly having 2 acceptance methods. Acceptance by empty stack, acceptance by final state. Here is the major difference you can find in pushdown automata compared to other automata. You take the example of finite automata, take the example of Turing machine, anything, they will accept strings with the help of final states. Good evening, welcome. So here the difference of pushdown automata comes here is, it is having empty stack method. This empty stack we cannot find in finite automata Turing machines. They are accepting by the way final state is reaching. If the strings are reaching in final state, then strings are accepted. But the difference between those automata and pushdown automata is, language accepted, strings accepted, even the final states are not there. This is the beautiful point here. Pushdown automata accepts strings without final states. Pushdown automata accepts languages without final states. How that is possible? Yes, that is possible in the PDA, but this type of things we cannot observe in the finite automata. That is the greatness. Anyhow, yeah, final state method is acceptance from final state is a universal method. So final state is anyhow there. Acceptance by final state mechanism is anyhow there. 2 methods exist to accept strings here, empty stack, final state. We need to habituate both the things. Questions are there in the exam from both of these. If you see, sometimes acceptance methods by empty stack, sometimes by final state. We need to habituate both of this. So that's when the classes also will study the way of acceptance by empty stack, how to construct, and how to construct a machine by final state. But this empty stack final state mechanisms are not same in the case of DPDA and NPDA. In NPDA case it is different, DPDA case it is different. Those things also we'll study in the coming classes. Then we have one more thing we studied previously. Whenever you say pushdown automata, We have non-deterministic nature and we have deterministic nature. Deterministic pushdown automata, non-deterministic pushdown automata, DPDA and NPDA. Right. So now the thing is, so non-deterministic pushdown automata, deterministic pushdown automata. Whenever we have two things, that too especially in automata or machines, we need to perform a comparison. So which is a more powerful here? Whereas in finite automata, DF and FA power is same. That is expressive power. Power is same. But here the power is different. That too NPDA is more powerful. Expressive power of NPDA is more than DPDA. This is just a recap. All these things we studied. Yes, NPDA is more powerful. Right. Now the question is, if they asked construct PDF for this language, he will not mention anything about this. Construct DPDA, construct NPDA. By default, what is our PDA? DPDA or NPDA? Whenever not mentioned about particular automata, just ask it to construct pushdown automata. The default automata comes as deterministic or non-deterministic. Which is the default one? So here power is more here. NPDA, yes, the default one is NPDA. Default automata, whenever you want to say PDA. Right. So based on this different things, the language of PDA also divided into two categories. DCFLs, language accepted by PDA context free language, are also categorized to two things: deterministic CFLs, non-deterministic CFLs. So these are generally called as CFLs. So we have one more category, that is DCFLs. The powers of machines are same. That's why powers of this language also changes here. Here it is DCFL comes. Here our CFLs comes. So DCFLs becomes subclass to the CFLs, because our DPDA is resides here, deterministic PDA resides here, your normal PDA, NPDA resides here. Based on different powers of the automata, the classification of the language is like this. So every CFL need not be DCFL. Every CFL need not be DCFL, but every DCFL should be CFL. This is what the understanding from these things. How this conclusion is coming, for that proof also we are going to study in today's session. That's all. This is what we studied in the previous class. Now we have a limitation. Whenever we are constructing, there is a limitation. If more than one memory whenever required, PD also fails. There are some languages for which PD also cannot be constructed. So we have a best example here. Look at this language. More than one comparison, generally that is more than one stack is required. In order to handle these comparisons, only one stack is not sufficient, more than one stack is required. So PDA not possible for this. This is a limitation of PDA. So PDA accepts some type of languages which are having comparison, but PDA also not accept all kind of languages which are having comparison. If more than one comparison, more than one memory required case, PDA also fails. This is the limitation of the PDA. So PDA not possible for this. Right. So like this is the overview of PDA, block diagram of the PDA, finite automata plus stack, formal definition of the PDA, acceptance methods of the PDA, and then the limitation of the PDA. Today also let us try to construct. Yesterday we have seen one example how to construct. Today also let us try to construct the PDA. Anybody having any doubts in yesterday's session in the construction point of view? Because in yesterday we have taken one example, A power and B power example, constructed the PDA. Today's session is all about construction only. I will make you, I think of the first example, there is a possibility of having some confusions. So to avoid all these confusions, let us construct some more examples. That is what we are going to study, and I will give the differentiation between how deterministic and non-deterministic PDAs, completely showing different transitions in today's session. Right. So we need to construct the pushdown automata for the given language. So this is our language. Number of A's and number of B's should be equal. There is a lot of difference between yesterday language and this language. Yesterday's one is, that is A power n, B power n. Yesterday's language is A power n, B power n. Equal number of A's and B's, but here the language is A's followed by B's. Number of A's followed by number of B's. But here order can be anything. So let me write the language first. How this language looks like. Epsilon is allowed. AB allowed. BA also allowed. But BA is not present in the previous language. AB allowed. BA allowed. So order can be anything. Your string can present in any order. So it can be increasing order, order A's followed by B's, B's followed by A's. Any order is allowed. But the thing is, number of A's and number of B's should be equal. Now we need to construct the pushdown automata for this. Right. What I told you in a previous class, to construct the PDA, what is the first thing required? We need to make a logic. First logic is required. In order to accept these type of strings, we need to make a common logic, generalized logic. That logic will accept all type of strings present in this language. How many strings present in this language? How many strings present in this language? Definitely infinite number of strings. So in order to accept all these infinite number of strings, we need to construct one common logic. So let us try let me frame this logic initially with some rough example. Then we'll make it systematically by transition diagram and transitions notation. My logic for this language is, whenever number of A's are encounters, I am constructing the logic for this in this way. Take this string AB. This is there in the input. Assume roughly this is the PDA. What is the logic? I need to check A's and B's are equal or not. Number of A's and number of B's are equal or not. So whenever A is coming, push into the stack. Whenever A is coming, push into the stack. Or whenever B is coming, push into the stack. Initially, we don't know initially A comes or B comes. Initially A may comes, initially B may comes. Initially whatever is coming, push into the stack. Right. So here A is coming, push into the stack. After that, how the PDA will take the decisions? PDA takes decisions based on reading symbol, based on reading input symbol, and based on top of the stack. Top of the stack. If reading input symbol and top of the stack are different, then PDA has to perform pop operation. Same, then PDA has to perform push operation. This is the what logic is. This is the way we are making a logic. So this logic will accept these type of strings as well. See here. This is also valid string. A's and B's are equal. Order is not important. Any order can be okay. So if B is coming, push into the stack. Again B is coming, but top of the stack is B. Input symbol and top of the stack are same. Whenever input symbol and top of the stack are same, what we need to do? Symbol and top of the stack are same, we need to perform push operation. Whenever symbol and top of the stack are same, perform push operation. Right. Now, whenever symbol and top of the stack are different, perform pop operation. So 1A, 1B pop out. For 1A, 1B pop out, like this. So this logic will work for all valid strings which present in the language. So let me repeat this logic once again. Initially A comes or B comes, push into the stack. Initially A is coming or B is coming, push into the stack. After that, reading symbol and top of the stack are same, push, different, pop. So the logic is, for same we need to perform push, for different we need to perform pop. So this is the logic. Now I need to implement this logic by using our transitions. Initially I am interested to show this construction for this language, PDA construction for this language by transitions. Then we will move to transition diagram, because both these notations are important. So whenever you are constructing by only one, assume you are practicing only for transition diagram. In the gate paper they may ask transitions notation, then it is difficult for you. That's why let us try to habituate for 2 or 3 examples for both, then we can stick to any one. Right. So what is the logic here? The first point is, initially A encounters or B encounters, push into the stack. Start from Q0. Whatever my logic is saying, that logic I am directly representing by transitions. What is the logic? The initial configuration I am observing here. Initially I am in state Q0. My state is Q0. Input is A. Top of the stack is Z0. So PD always take decisions based on 3 things. What is your present state? What is your reading symbol? What is your stack symbol? Based on these 3. So I am in state Q0. My reading symbol is A and my stack symbol is Z0. Now after observing configuration, what is your logic? The logic will represent in the right side. What is the logic saying? Initially, whether it may be A or B, we have to do only push operation. For initial symbol, push operation. So represent push operation. If I show this together, that is called as push operation. So Q0 AZ0, Q0 BZ0. If you represent this together, that is comes under push operation. What is the next one? Next logic is, after initial symbol, whenever second symbol is coming, second symbol, then we have to see top of the stack. Reading symbol and top of the stack both are same. This is one possible situation. Reading symbol, top of the stack are different. This is one possible situation. So let me write these 2 situations first. For them transitions. We are in Q0. The second symbol is assume A. The top of the stack can be A. Reading symbol, top of the stack, both are same. Assume that one. This is one possibility. Next one is reading symbol, top of the stack are different. This is one more possibility. So these are the all possibilities encounters while we are constructing our machine. Initially A encounters or B encounters. We have to perform push operation. Then reading symbol, top of the stack are same. Reading symbol, top of the stack are different. So now what is the logic? Whenever reading symbol, top of the stack are same, then the logic says same case push, different case pop. So reading symbol, top of the stack same, then perform push operation. Reading and top of the stack are same, perform push. Here also reading and top of the stack are same, perform push. Reading and top of the stack are different, perform pop. Staying in the same state, different, perform pop. So that's all. This is the PDA. And last one is acceptance. That is from the same state, input is ended, Z0. So after performing 1A, 1B pop, 1A, 1B pop, like this if you are doing, whenever string is ended in the input, if all the elements are popped out from the stack, only Z0 means what? For my 1A, 1B is there, for my 1B, 1A is there. That is what required for us. So then we have to go for acceptance. That's why in this process, epsilon indicates end of the string. If it is end of the string is coming, nothing is there in the stack. That means everything is popped out. 1A, 1B popped out, 1B, 1A popped out. If that is happening, this is the acceptance. Then you go for acceptance by entering into final state. Move to Z0. This is the PDA. So what is this? This is the initial possibility. Initial possibility. Then this is input and stack are same. Same. Input and top of the stack are same. Then push operation. Then different. If they are different, then this is. So logic same. Whatever the logic previously I am saying orally, I am implementing it by using transitions. Getting? So initial possibility, whenever they are same, whenever they are different. Last one is acceptance. I am using acceptance by final state method. How this PDA looks like? Is it scary or easy? Any opinion on this? Just if any new students are there, watch yesterday's recording once, then try to understand this. Very, very easy. Don't have any confusions. Logic is the main thing. So manual logic, how you are thinking about the strings, you are thinking we are putting on paper. That is a PDA construction. So what we will think about the strings, what we will think about nature of the strings. Same thing if we show by using logic in these transitions, that is our pushdown automata. Right. So this notation is called as transitions notation. It is a transitions notation. The similar way we will go and study transition diagram notation. If I write all these transitions in diagram format, how it looks like. First transition, initial one, initial possibility. Initially A encounters or B encounters. Initially A encounters or B encounters. Push operation only. Push into the stack. Push into the stack. Initially A comes or B comes, push into the stack. What is the next one? Then whenever they are same, input symbol top of the stack same, input symbol top of the stack same, then also we have to perform push. Input symbol top of the stack same, input symbol top of the stack same, push. And then input symbol top of the stack different, input symbol top of the stack different, then we have to go for pop. Input symbol top of the stack different, A on B, B on A, then go for pop. From this, whenever epsilon encounters, epsilon Z0, then keep the Z0 as it is, final state. So this is the PDA to accept the previous language in transition diagram. So in the next example onwards, see, we are in a basic examples. So first constructing this, then converting into previous one. But for some examples, directly we can construct transition diagrams also. For some examples, we'll practice only constructing transition diagrams. Because we are in initial stages, so slowly we are constructing. Once it becomes easy for you, then we'll construct any one of this. For the same language, we can show by using transitions or we can show by using diagram. Because for every language, both can be possible. So this is the way we can construct pushdown automata for given language. Right. This is a PDA acceptance by final state. Same thing we can do by acceptance by empty stack. But whenever it is empty stack, small changes are there. Let me explain for the same example how to do by empty stack method. If we do the same thing by empty stack, how it looks like. So here it is empty stack, then we have to stay in the same state. Only last transition changes, all the remaining thing is same. So the last transition is for empty stack, stay in the same state Q0 and make the stack empty. Whenever it is empty stack, we have to empty the stack completely. That's why we have to pop this Z0 symbol as well. Pop the symbol Z0 as well. This is empty stack. So what is final state method? In final state method, automata has to reach final state, definitely. See, here also strings are accepted. The beautiful thing in this mechanism is, here also strings are accepted, language accepted, but we don't have a final state. So without having final state, Just by making the stack empty, we are accepting languages, we are accepting strings. That is called as empty stack method. So if I show this in the diagram, how it looks like. So same Q0, whenever epsilon Z0 encounters, make epsilon. Epsilon Z0, make it as epsilon. All the remaining things are same, only whenever it comes to this. So what is this one? This is the initial possibility. This is same, whenever reading on top of the stack same, this is the possibility, whenever they are different. This is the possibility. Initial, same, different. Right? So acceptance by empty method, acceptance by final state method. For this example, I have explained you both. Here see, the construction is not a much difficult one. Only notation is seems to be new one. If you are habituating, if you solve, if you practice 3 or 4 examples, it becomes easy. The major concept here is identifying logic. So whenever you see that language, immediately identification of logic is the main thing here. The fundamental thing is identification of logic. Right. So let us try to understand, let us try to construct for some similar language. I hope this is the way how we constructed for this is, and you understand how it is completely different from this a power n, b power n. A power n, b power n is a different one, and this, that is a equal number of a's followed by equal number of b's. Equal number of a's followed by equal number of b's. But whereas this one is number of a's and number of b's are equal, order can be anything. So for this we constructed with only one state, but for that previous one a power n, b power n, 2 states required. So number of states completely varies from language to language. Number of states is completely depends on the type of language for which we are constructing the pushdown automata. Right. Let us try for this. Construct PDA pushdown automata for this x such that number of a's of x greater than number of b's of x. What is the difference between previous one and this one? In the previous one, number of a's and number of b's can be has to be equal, but here number of a's should be more than number of b's. Number of a's should be more than number of b's. So let us understand what type of strings exist in this language. So the strings of the language can be epsilon not allowed, only a allowed, and then 2a's 1b. Order is not important. 1b 2a's allowed, ab a allowed, ab. So all this take in any order. String can start with a. The string either can start with a or string either can start with b. It can start with a or it can start with b. Order can be anything. But finally, if you read number of a's and b's, a should be more. Number of a's should be more than number of b's. So whenever you see any language like this, the first thing what you have to do is find out the logic for this. What type of logic is required in order to construct pushdown automata for these type of strings. So whenever anybody watching, or whenever you are watching this in the recording time, pause for some time and try to create a logic by your own. Try to create a logic by your own. For what type of logic? This type of strings will be accepted. The same logic, if we show by diagram or transitions notation, our PDA is ready. So first thing is, let us make logic ready. Let us make the logic ready here. So the logic is same as previous logic. Same as previous one. So need not to create any new logic, same as previous one, small changes are there. Same thing. Initially, what is the previous logic? Initially, A comes or B comes. The initial reading symbol is A or B. First push into the stack. Initial symbol is either A or B. First we have to push into the stack. Then whenever reading input symbol is reading input symbol and reading top of the string symbol are same. Reading input symbol, reading top of the stack symbol are same. Then we need to perform push. So for same situation case, we are performing push operation. Whenever reading symbol, top of the stack symbol are different. So reading symbol from the input, top of the stack symbol are different, then we are performing pop. Pop. Until this same. But whenever epsilon comes, situation is different. Let me explain that through some example. Take the string A_B 3s. Let us try to understand the logic first. If I want to accept this, so what I am saying is, apply your same concept of previous equal number of A's and B's. What to do? Initially A is encounters or B encounters. Initially A is reading or B is reading, first push into the stack. For the initial symbol, we need to push into the stack. Then whenever second symbol we are reading, for the second symbol and top of the stack. Symbol is B, top of the stack is A. Reading symbol, top of the stack are different. Then pop. Reading and top of the stack are different, then pop. So here we have to pop. Then B is coming. Push. Reading symbol, top of the stack are different. Reading symbol, top of the stack are different. Then pop. Then next, till this over. A, push into the stack. Now once the string is ended, epsilon. Whenever the string is ended, epsilon comes. Whenever we are reading epsilon from the input, the meaning is string is ended. Here the difference is there in the previous example and this. So in the previous example, there are equal number of A's and B's. Whenever we are reading epsilon from the input, what is the stack symbol there? Z0, 1B, 1A pop, 1A, 1B pop. If we are continuing like this, whenever string is ended, top of the stack is nothing, that is Z0. Everything is popped out from the stack. But here number of phase more means whenever epsilon encounters in the input, whenever we are reading epsilon in the input, definitely one A should be there in the stack, at least one A. At least one A should be there in the stack. What does that mean? Even though my input is ended, still A is present in the stack, means number of A's are more. This is the logic. So the logic clearly says that whenever my input is ended, still A's are present in the stack, means for these A's, whatever present in the stack, for them B's not exist in the input, means definitely in this string number of A's will be more. So this is the logic. So logic is very simple, same previous logic, equal number of A's and B's logic. The additional thing is in that whenever the string is ended, whenever epsilon is there, still A is present in the stack. That can be one or more A's. That is our valid string. Then accept it. Right. So now logic is ready. Once the logic is ready, what we will do? Construct the machine. So let us try to construct this machine for this. If I show in the same one, in the previous one, same. Up to this, it will be. The initial situation is same. Reading symbol are same. Push operation. Reading and top of the stack are different. Pop. Till this part, no doubt. So for initial situation is same. Reading top of the stack, same case like this. Different case like this. The last one we need to change. That is for epsilon. So now first let me check for let me construct for final state method. Epsilon A comes. Don't perform any push pop, otherwise you can perform pop, not an issue. Immediately enter into final state. Immediately enter into final state, because what is my conclusion? Input string is ended. Once the input string is ended, still A's exist in the stack. That means whatever the A's are there in the stack, for those B is not present in the input. If B is not present in the input, definitely your number of A's are more than number of B's. I came to that conclusion. So based on this conclusion, I am accepting the string by reaching the final state. So that's all. This is the additional transition if you want to accept by final state for the previous language. If you construct like this, now this will accept X such that number of A's of X greater than number of B's of X. To accept this language, this is the case. Now the same thing, let me construct by empty stack method. Empty stack method. So in the empty stack method, what is the situation? We don't have final states. Whenever we have A's in the stack, still it is empty. So if it is empty stack, need not to enter into final state. Final state is not required. Not necessarily to enter into final state. We will accept the strings only by staying in non-final states. We will accept the strings That is a beautiful concept. We will accept the strings, but final states are not there. Without having final states, acceptance is called as empty stack method. So let me show this. If it is an empty stack, how it looks like. In case of empty stack, all this is same. Whenever on epsilon A, input is ended, still A's are there, we will come to Q1, state Q1. This is not QF, it is Q1. QF, Q1 both are different. Q1. Then there can be, then in the empty stack, we have to make the stack completely empty. Empty stack meaning is we have to make it completely empty. So all A's pop out from the stack. Pop out all these number of A's from the stack just by epsilon on A pop, epsilon on A pop by staying in the same state. And finally, the epsilon Z0, make that also pop. So final state not required here. Final state not required. So if you make the transitions in this way, this will accept the same language as our previous, number of A's greater than number of B's. So this is the pushdown automata for our language. Number of A's of X greater than number of B's of X. Right? Similar one, small changes. Logic is same. This logic is same as our previous one. Equal number of A's and B's logic. What is the difference? The difference is whenever epsilon is the input, that is the input is ended, there Z0 comes in the stack, but here A comes in the stack. If on end of the input, if A is present in the stack, that is our valid string. We have to accept. If it is acceptance by final state, by reaching final state, we will accept. If it is acceptance by empty stack, by reaching one non-final state Q1, just by adding 2 more transitions. That is the meaning of first transition. This is in empty stack method, we have to empty the stack completely. That's why all number of A's present in the stack you pop out. So on epsilon only, input is epsilon, every A pop out. Stack, read A from the stack, pop, read A from the stack, pop. Then whenever Z0 comes, pop that. Now stack is completely empty, halt the machine, say accepted. So like this, even though we don't have any final states, the strings are accepted by empty stack method. Okay, right. So like this, if you practice some few examples of this kind, then your construction confidence improves in PDA constructions. So for just for one example, 2 examples, no. For initial example, anyhow, every student will confuse. Just by practicing 3 or 4 examples, you will feel perfection. You will feel comfortable. And how these transitions we are mentioning. See, for this transitions, I am not showing anything. So directly transition diagram. So in similar way, for the next coming example also, we will focus completely on transition diagram. We don't construct transitions. We will take the logic, from that logic directly transitions, transition diagram notation without any transitions notation. So this is our next example. A power n, A power m plus n, B power m, C power n. So the logic is clearly here. The language is nothing but number of A's should be equal with number of B's and C's. Number of A's should be equal with number of B's and C's. So the sum of B's and C's should be equal to number of A's. Right. What could be the logic for this? Seems very easy. How we can frame a logic? So the type of strings are generally, assume 5 A's are there, 2 B's, 3 C's. These type of strings. So the construction of PDF, for that the minimum required thing is first construct logic. Let me construct the logic first. Logic. So board management also important here, because these diagrams looks bigger one. So I'm writing this side, logic this side. Whenever A's we are reading, B is reading what to do, C is reading what to do. Whenever A is reading, push. Whenever A is you are reading, push into the stack. All A's push into the stack. So this thing should be equal with this thing. So comparison is going on. For this comparison between A's and B's, C's. All A's I am remember in the stack. For B, A's pop out. For C's also A's pop out. So for B's, pop. For C's also pop. Pop what? A's only. Pop A's from stack. So logic is clear. Now show the same thing by using transition diagram method. For this we are focusing only on diagram, not interested in transitions. So let us start this from state Q0. What is the first one? A's are coming, push into the stack. So initially 1A, or any number of A's. So in the logic, if you want to implement this, A's push. Initially A's are there, also push. After that any number of A's are coming, also push. All A's push into the stack. Then B. For B's, pop A's from stack. So for B's, pop A from stack. After that, how many B's? There can be so many B's. Then for every 1B, 1A pop from stack. So assume all the B's are over. Then C comes. For every 1C, what is there? Even C's are coming, still A's present in the stack. A's are more here. So pop out from the stack. Then for every 1C, 1A pop out from the stack. So first C, A's are there, pop out. Every 1C, 1A pop out from the stack. Then finally epsilon comes, Z0, final state, by making Z0 as it is. So this is a PDA. Same logic. See here, copy paste logic. A's are there, push into the stack. These transitions. B's are there. For B's, A's pop. B's are there. A is there in the top of the stack, pop. This epsilon indicates pop operation. For all B, 1B, 1A pop, 1B, 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 1A pop, by staying in the same state. Assume B is completed. 1C, 1A pop, 1C, 1A pop, like this, by staying in the same state. In this process, whenever epsilon comes, so if whenever A's and B's and C's are equal, what is there in the stack? Z0. That means for B's, A's pop out, for C's, A's pop out, C's are ended. My stack has to be empty. Stack has to be Z0. Then only valid string. That's why whenever ended, input is epsilon, Z0 accept by reaching final state. So this is the easy. So the main thing remains here. The logic is the major one here. Once you are able to identify logic for the language, the construction of PDA is nothing. See here, we constructed in a few minutes, 1 or 2 minutes you can construct. Transitions not required, diagram is enough. Transitions also not requires much time. So whichever one you feel comfortable, you design that one. But both are important for examination point of view. In the examination, sometimes we may get transitions. Sometimes they will show PDA by diagram like this. Anyhow, whatever it is, the way of construction of PDA is this much simpler, this much easier. It's not any great thing. So I hope you understood. In today's session, we constructed pushdown automata for very important languages. I feel you are happy with this construction. You are familiar, you feel very easy with this construction. Okay. That's all, students. That's all about today's session about construction of pushdown automata. I hope you enjoyed the session. We'll continue with some other topic in the next session. Thank you. See you in the next session. Bye bye.